has something, it's more appropriate for long-term growth because it has a limit to growth. So I don't know, I mean, hopefully you remember, this is exponential growth, right? And this is exponential decay. But Logistic has a horizontal asymptote, and we call it like the carrying capacity or the maximum sustainable population. So it looks exponential, but then it starts to level off. So logistic function looks like that. Its differential is a little bit different. So what I'm going to have us do is write it down. Like I said before, this one you don't need to memorize. I'm going to write it in terms of P just because typically, really, we're going to use it to model populations. Okay, so we would have dp dt, so the change, or rate of change in population as compared to time is some constant times P times capital M minus P. Okay. It would involve writing things, it would involve separating fraction, or separating the variables, and it would be a lot more complex than when we did that with exponential. Remember how we just took the derivative of both sides? Well, this would, you would get a fraction, and then you have to do, it's called partial fractions, which this year I'll get to it in pre-calculus. Unfortunately, you guys, because of last year was a unique year, we didn't get to it. But that's why I was saying I'm not going to show the derivative because I haven't. Just trust me that it's hard. It's complex. It involves something that is not an AV topic. But it can be shown that if you would do that, if you would separate the variables like we did the other day, find a constant, that what the initial equation or population equation would be is capital M over 1 plus A E to the negative M times K times T. So let's write that down, and then we're going to kind of put some comparisons so you can see what those things stand for. So do you remember when we did logistic equations before? It was a while ago. What this top number was? That was the maximum carrying capacity, and so that's that horizontal asymptote there. So I also want to point out to you that that is right there. Where does the K show up? So we have K right here. Do you see that that is K there? Also the M goes here and here. So really if you had the differential, you would take those two pieces, and then you might be asking yourself, well, there's still one other thing that we have to find. What is it? Well, I would be given M, I'd give you K, A, and so the way that you're going to find A is you're going to use, it is not the initial value, but you're going to use the initial condition to find it. Okay. Do you guys have this written down? So then let's do one. The moose population, ooh, and moose is plural for moose. The moose population in a state park, it is not meese, it's moose. The moose population in a state park from the year 1987 can be modeled. You are writing this down. Oh, now you are. Now you are. By the differential equation dp dt equals 0.0003p times 1000 minus p. If the initial population was 61 moose, find P of T.
What? It's 101 in the initial population. Wait, what? Oh, if the initial population was 61. Oh.
So what I'm going to do is I'm going to go ahead and I'm going to highlight the things like from above that are important, which is this and this. And I'm going to put those two things in the appropriate spot in the equation. So from above, that 1000 is going to go up here. The 1000 is also going to go here, and then the k is going to go here. I don't know a yet. So P of T equals 1000 over 1 plus A times E to the negative. Okay, can we go ahead and, are you, up here has to be M times K, right? Can we just do that instead of writing 1000 times 0.003? Can you do that for me? If you did that, wouldn't it just be 0.3 P? Are you guys following? Okay, so once you're done with that point, what you would do is you would use the initial population to generate an equation to solve for A. Okay, so in this equation up here, it is negative M times K times T. So negative 1000 times 0.0003 is negative 0.3. Isn't it? Well, can't you just move the decimal over 3 places? 1, 2, 3.
Oh.
So I'm gonna use the initial value. An initial value means that T is 0, and I'm gonna plug that in. So that gives me 1000 over 1 plus A. Why does it give me just 1 plus A? Because when I do this, this would give me e to the 0 power. And what's e to the 0 power? 1. Okay, so what I'm going to go ahead and do is I'm going to put that 61 in here, and I'm going to solve that equation. So 61 equals 1,000 over 1 plus A. I'm going to multiply both sides through by 1 plus A. That cancels. Remember, I'm trying to solve for A. You could distribute if you want. I think it would just be easier though to divide by 61. So if I divided both sides by 61, I would have 1 plus A equals 1,000 divided by 61. We'll use our calculators in a second. Finally, what would I have to do? Just subtract 1? Cole, stay with us, man. I don't want to have to explain this later. All right.
Oh, man.
What do you get with that?
$15.393.
Great. I'm so glad that you wrote it as 3 decimals, because that's how we want to round things. All right, finally, then we would just put our equation all the way back together. So the only thing, remember, missing from this was that A. So my population equation is P of T equals 1,000. I can fit it in. I know I can. Over 1 plus 15.393 to the E, or E to the negative 0.3 T.